Yes, she was thoroughly traumatized.
Progress. Recording.
Probably not discharged. It definitely went. I'm so sorry.
Progress.
First, are there any questions or concerns?
Yes, I have a question.
Go ahead. Toyin, what's-
My question is, when I go to BOHR models of atoms,
say it one more time. I'm sorry, say it one more time.
both models of atoms.
Okay,
So when I go to phosphorus, so the electron there were 15. So I don't know how they got 31.
you know what? Do you remember we talked about the fact that, so that's the protons are 15.
Yes.
Yeah, that's a really good question. The protons are 15. When we add the number of neutrons, it should be 30, right?
Yes.
Okay, well, what if there's an isotope involved with phosphorus? How would that change that mass number? Or the atomic weight? Toyin, what do you think?
I don't know.
Well, tell me, let me ask you this. Define the mass number?
Mass number, I think is the total number of the electron.
No, but it's the number of protons
Number of protons is
Plus what?
Mm.
Go back, you can even Google it, Toy, and tell me what the mass
Yeah.
number is.
Progress.
total of protons and neutrons in the, and neutrons in the nucleus.
Right. So normally the number of protons equals the number of neutrons, right?
Yeah.
Well, what if it's an isotope?
Then,
Then what, Kevin?
oh, sorry. It has a different
That will be
number.
different neutrons.
It
Yeah.
has a different mass number.
Yes.
That's why that has 31. Is it might be possible, it's possible that the isotope is the most common form of that atom. That's why that's given as the mass number.
Mm.
Does that make sense?
Yes, yes.
That, Toyin, that's a really good question. I'm impressed because I got asked that and it took me a little while to figure it out the other day. But that's the question. That's so what she's referring to. Let me come back here. It's a really good question. I'm impressed with that one. Let's see here. Because that's a harder, I always like questions, but that one is one that, yeah, you don't, it's a little harder to wrap your head around. So bear with me just for a second here. Go back up. I have to remember where it was. Okay, right here. This is what she's referring to. It's right here. All of the others, we know that hydrogen doesn't have a neutron in its most common form. Carbon has 6 protons, 6 neutrons. Here, this is the mass number. The bottom number is the atomic number. 14 has 7 neutrons, 7 protons. Oxygen has 8 neutrons, 8 protons. Phosphorus has 15 protons, but it says here that the mass number is 31, or the atomic weight is 31. It's because on average it might be, or this is the only way to explain this, that the most common form of phosphorus has 16 neutrons rather than 15. Now I'm going to move up and I have to remember where we were. This doesn't show me the slide number. If you can see, we are a little behind. We will not finish chapter 2 today. It's a long PowerPoint. It's a long chapter. But I also feel like it's probably one of the hardest ones to grasp. And it's the hardest one to wrap your head around. And so I would prefer to take our time with this, and I'll extend out deadlines. But I want to take our time with this one. When we talk about the cell one, it's a lot easier. This is that, this is what it does, so forth. This one isn't like that. So I want to take our time a little bit with this. Trying to remember where we were.
We just finished up the polar molecules.
Okay.
I think it's like slide 53. I don't know. If
Yeah,
it
but
tells
you know, this doesn't, this little screen that this has on D2L doesn't tell me what slide the number this is.
Oh, great.
I know, that's what's fun about it.
We
I
stopped at
was-
molecular polarity on page 53.
Were we about right here?
Yes.
Yeah.
Okay, let's start right here. So when we have a molecule that is, when we have a molecule in which we have an atom like oxygen that's highly electronegative bound to an atom that is not as electronegative, the result is that we get a polar molecule like water. And remember, electronegativity is the force that a given atom has on pulling electrons towards it, towards itself. So the greater the electronegativity, the greater that atom's ability to pull electrons towards itself and pull them off other atoms towards itself. Oh, I think we went too far. I'm sorry, give me 1 sec. I don't know why this is so hard. It's because it's a big PowerPoint. Give me 1 second. So the result is that the oxygen has a partial negative charge on it, and the two hydrogens, because they don't have the negative charge on the electrons balancing them out, they're partially positive because they're essentially an exposed proton. The electrons, both of hydrogen, are spending more time around the oxygen. So the oxygen has a partial negative charge. The hydrogens have a partial positive charge. So this is how any polar molecule works. There's a partial negative charge and a partial positive charge. If it's nonpolar, the electrons are being equally shared. So nonpolar molecules involve covalent bonds where the electrons are being equally shared. Polar molecules involve covalent bonds where the electrons are not being equally shared. And the whole reason you have polar molecules is because you have an electronegative atom that is bound to another atom that isn't as electronegative. And the result is that the electrons spend more time around the electronegative atom than they do the atom that isn't as electronegative. Or we can call that an electropositive atom. Electropositive meaning that it tends to take on a more positive charge. So this is the first textbook. Your textbook is the first textbook where I've ever heard the term electropositive. I think I'm not sure I like it. But it's just telling you that it's the opposite. It takes on more of a positive charge, that atom. So the result is that polar molecules have this partial separation of charge, or a dipole. In a solution, because we know that opposite charges attract, polar molecules will orient themselves so that their partial positive charges are closer to the partial negative charges of other molecules. So if you look for, this is one molecule right here, this is one molecule right here. Partial positive charge of this molecule is oriented towards the partial negative charge of this molecule. Water, with its partial positive charges and partial negative charges, orients itself around a sodium ion. When sodium chloride is dissolved, orients itself around a sodium ion so that its partial negative charge is closest to the positive charge of the ion, and the positive charges on the hydrogens, the partial positive charges on the hydrogens, are furthest away from the positive charge on the sodium. Now this is important because this is how hydrogen bonds result. Hydrogen bonds form when a hydrogen atom that's already linked to an electronegative atom is attracted to another electronegative atom so that a bridge is formed. So the partial positive charges on the hydrogens are attracted to the partial negative charges of another electronegative atom on a different molecule, forming a bridge. Let me say that one more time. A hydrogen bond is formed when the partial positive charge on a hydrogen that's bound to an electronegative atom is attracted to another electronegative, to the partial negative charge on another atom of another molecule. These hydrogen bonds are important for intramolecular bonds, which help molecules to maintain specific 3D shapes and structures. Rather than saying shape here, let's say structure. Because if you remember, we talked a lot about how structure and function are important and how they're related. So hydrogen bonds are really important in maintaining a molecule's structure. And therefore allowing for the function of that structure. So hydrogen bonds, serve as links between molecules. They also help maintain the 3D structure of large molecules, like proteins, DNA. The DNA double helix is held together by lots of hydrogen bonds. Water is held together. Mom, will you bring me my bottle of water that's sitting by the sink?
What's that?
Will you bring me the bottle of water that's sitting by the sink? Sorry, I have a teaching assistant. My classes go a lot better when she's here. So water is held together by the hydrogen bonds within it. If it didn't have hydrogen bonds holding individual water molecules together, it would become a gas. And it would immediately vaporize. We'll talk more about that in a second. So oxygen is electronegative, hydrogen is electropositive. Remember, electronegativity is the force of an atom. It's pulling force for electrons. Hydrogen is electropositive. This means what?
I think it's either A or D.
It's
I'm not
either
sure.
what?
A or D. I'm not sure.
Okay, so oxygen, remember that's the more electronegative element. It's a more electronegative atom. So is it gonna pull the electrons more its way? Yes. So the oxygen pulls the electrons away from the hydrogens that will then become more positive. Or we can use it this way. This word is kind of worded a little wrong, this question. Because if we put here, if we say the oxygen pulls electrons away from the hydrogen, which is what happens here, and the oxygen becomes more negative. Or let's put it one other way, the oxygen pulls electrons away from the hydrogen and the hydrogens become more positive. I think the answer is C, but it depends on how you want to word it. Not a very well worded question. If I was giving this on an exam or a quiz, I would give you either C or D because it depends on what's becoming more negative and what's becoming more positive. So one last type of bonds. Do you remember the other two? So we have ionic bonds, we have covalent bonds, and we have hydrogen bonds. One more type of bond. We have a van der Waals bonds or van der Waals forces. If you remember at the very beginning of this chapter, we talked about how the electron cloud around an atom is it's not so much in the orbits or in the shells as the electrons actually move in a cloud. Do you remember that? That we can't at any given moment pinpoint where a specific electron is. We know on average it's within those shells, within the orbits of those shells. We know on average that's where it is. However, we can't pinpoint exactly where it is at any time. Therefore, we know that the electrons actually move like a cloud around the nucleus. With that in mind, that's the basis of these van der Waals forces. Because atoms around the electrons around the atoms show random fluctuations in their density, rendering one side of the atom more positive and one side of the atom more negative at any given moment. So just like a polar molecule or a covalent or a let's say a polar molecule, this is acting like a polar molecule where at any given moment, there's a partial positive charge on one side and a partial negative charge on the other side of the atom. Just because of the random fluctuation of the electrons. And the atoms will orient themselves so that the opposite charges, these opposite partial charges, are closest to one another. These are the van der Waals forces. Don't ask me where the name van der Waals came from. I'm guessing it was the person who discovered them. These forces, even though they're really slight and they're not very strong, these forces are important for protein folding and the binding of proteins to each other, such as a receptor to a ligand or such as a hormone. And the interactions of lipid molecules within cell membranes. Here's a summary of all of the bonds that we've talked about. So we have ionic bonds. Remember, that's where one atom gives up an electron completely to another atom. Or another atom takes on an electron completely from a different atom. Covalent bonding is a sharing. We can have single covalent bonds where one pair of electrons is being shared. We can have double covalent bonds where two pairs of electrons are being shared. We have nonpolar covalent bonds where they're being equally shared, the pairs of electrons. We have polar covalent bonds where they're being unequally shared. One atom is more electronegative than the other one. And we have hydrogen bonds where the partial positive charges and the partial negative charges of the molecules are resulting in hydrogen bonds. These always involve a hydrogen atom. Van der Waals is based in just the random density disturbances of the electron clouds around atoms that results in these opposite charges attracting. Now, my question for you, and I'm not sure if it's on the next slide or not. Actually, we'll move forward before I ask my question. Hydrogen bonds are similar to ionic bonds because of what? So hydrogen
Is
bonds.
it A?
Say
Yeah,
it again?
Is it A?
A.
Why do you say it's A, Kevin?
Because because we just discussed that the hydrogen has the electronegativity and it attracts the opposite.
And what does that result in?
But I don't
What-
know.
So tell me what makes up the hydrogen bond? How does that occur?
It's when partial positive is attracted to a partial negative.
And what's the partial positive charge on in a hydrogen bond? What part of the molecule is partially positive? Would you say the hydrogen is?
Sure.
Kevin, you're doing a good job. You're doing a good job. I'm making you think through this because I want you
are.
to make sure you understand.
You were totally right at the beginning. I have a hard time grasping this.
You're okay, but that's why I'm doing this to you. So just put up with me torturing you for a minute here. So the partial positive charge on the hydrogen is attracted to what on another atom?
The partial negative.
And why is that other atom that it's attracted to, why is it got an overall negative charge, partial negative charge on it?
Because it has an odd number of electrons.
Well, if it's an electronegative atom, what does that mean?
It has more electrons than protons.
Or it's
Sharing.
sharing unequally with another atom where
Okay.
it has more than the other atom does, resulting in a partial negative charge on that atom, right? Sound
Okay.
about right?
Yes.
Make sure if you don't understand, please just tell me you don't understand. And so now the partial positive charge on the hydrogen is attracted to the partial negative charge on this electronegative atom that belongs to another molecule.
Okay.
Does that work?
Yes.
Okay,
Partial
good
positive.
job. That was really good. So yeah, now you're never going to answer another question. No, you know what? I oftentimes when I teach, I will turn it around on you and ask you what your reasoning is behind your answer. And you did great. So hydrogen bonds are similar to ionic bonds because they're due to opposite charges. What's the difference between an ionic bond and a hydrogen bond?
Excuse me.
You said what's the difference?
Yep, what's the difference? This is
Ionic
how,
bonds are very weak, are pretty weak, and hydrogen are stronger because it
no,
forms.
reverse it, reverse it.
Okay.
No.
So ionic bonds are formed through ions where they're not, the atoms involved are not sharing electrons.
Okay.
They've completely taken on or given up an electron. And so they're not partial positive or partial negative charges. They're just negative or positive charges. They're not partial anything. Does that make sense?
So that makes it stronger? Well,
Yeah.
obviously, because it's not
It-
partial. Duh.
Right.
Okay.
So that's the difference. We know they're similar because opposite charges attract. We know the ionic bonds are stronger because the charges are not, they're opposite charges and they're not partial opposite charges. They're complete. Now so what were the 4 types of bonds that we've talked about? Someone tell me.
Ionic, covalent, hydrogen,
Ionic, covalent.
And what else?
and the van der Waals force.
Right. Good job. Which one is the strongest?
I would say ionic.
You're close. Ionic ones can get broken up in water.
Okay, well, maybe covalent because they're sharing.
You're right. They're sharing. Their covalent are the strongest. What ones are next? Someone besides Caitlin. If covalent ones are the strongest, what bond is next in its strength?
Ionic.
Ashley, what one did you, was that Ashley saying ionic?
Yeah, ionic.
Perfect, yes. What one is next?
Hydrogen.
Hydrogen.
Hydrogen, right. And the last one is the van der Waals. So water, moving on, you remember this is a very polar molecule. It's polar, it's got an oxygen and 2 hydrogens attached to it. It's very electronegative. So the oxygen's very electronegative. And it can also, and it hydrogen bonds with other water molecules because the partial positive charges on the hydrogens are attracted to the partial negative charges on the oxygen. So water is very polar and it forms hydrogen bonds with itself or other molecules that are polar. Depending on how molecules interact with water, they are described as being hydrophilic, hydrophobic, or amphiphilic. My first question is for you. What does hydro mean?
Water.
Hydro means water. What does philic mean?
Love.
It means love. It means love. So hydrophilic means water loving.
It means what?
Hydrophilic means loving. So sorry, let me back up, Toy, in 1 second. Hydrophilic is water loving. Water loving. In order to be hydrophilic and be water loving, you have to be polar too. Polar dissolves in polar because of those partial positive and partial negative charges. What does it mean to be phobic?
Scared.
Scared, kind of.
Be afraid.
If you think like a germaphobe, ew, 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 ew. I mean, we learned about cooties when we were really young, and now we have to try to avoid cooties again with the COVID. So hydrophobic means water, ugh, trying to stay away from it. If something is hydrophobic, it's non-polar. Amphiphilic or amphipathic means that a molecule has a polar side, a polar end to it, and a non-polar end to it. So it's half and half. In the next chapter, when we talk about phospholipids, and I think we talked about it a little bit in this chapter, phosphates are very hydrophilic. They're very electronegative, very hydrophilic. The tails, fatty acid tails are very nonpolar or hydrophobic. And so membranes will immediately orient themselves so that the polar ends are the only ones exposed to the water on both sides of the membrane. So water, it's also, it's your most crucial living, one of the most crucial living molecules. I'll say it is the most crucial. 60 to 80% of the volume of most living cells. Water has a high heat capacity. This thermal stability of water helps it to stabilize the internal temperature of the body because it can take on a lot of heat. Calorie, you see these on your food products. They're actually, it's a misnomer. The calories on that it says on your food products are actually kilocalories. So that which is 1,000 of a calorie. 1,000 times 1 calorie. So a calorie is the amount of heat required to raise the temperature of 1 gram of water 1 degree Celsius. A kilocalorie, which is what the calories are actually on your food products, is the amount of heat required to raise 1 kilogram, so 1,000 grams of water 1 degree Celsius. The high, another property of water is that it has a very high heat of vaporization. What this means is that it takes a lot of heat energy, 540 calories, to change water from a liquid state to a gaseous state, to a gas. So the high heat of vaporization is the fact that is because it takes a lot of heat to change water from water to gas. Why is that the case? If I show you this water, I'm going to stop sharing just for a moment here. Have this water like this. And like I told you, how is it being held together? Why is it actually a liquid and not a gas right here? You remember?
Because of the hydrogen bonds.
Yeah, the hydrogen bonds between each of the water molecules. What if I want this to actually go into a gas? What would I have to do?
Take out all the hydrogen.
I have to
bonds?
break all of the hydrogen bonds. Every time you break a hydrogen bond, one of those water molecules is released into the air. My last question, and this is going to be, I want you to think about this for a minute, is ice. If you've ever looked at ice on water, you put ice in a cold glass of water, does it sink to the bottom of the water or does it float?
It floats.
Floats.
Why does it float?
We were cited for having an expired yogurt. And
Why does it float? That's my question. Hold on to it for 1 second here. So high heat of evaporation because evaporation requires all the hydrogen bonds to be broken. The reason that we can be cooled off with sweat is because the water is secreted onto our skin, and then it becomes vaporized because it absorbs the heat from the body. And as it absorbs the heat from the body cools off. You keep removing heat from the body through the secretion of the water that then gets vaporized, resulting in a lower body temp. So sweating cools the body, and as sweat evaporates from the body, a small amount of heat is needed to break the hydrogen bonds, and as a result, the body temperature is lower. Remember, this is one of those homeostasis methods where your body works with water to actually bring down your temp back to where the narrow limits it needs to be in. Water also, because of its cool polar properties, makes it the universal solvent, makes it's able to form hydration layers around ions and around molecules, forming biological colloids, which we'll talk about in a little bit.
Can I ask a question just out of curiosity?
Go for it.
So have you ever like messed with dry ice?
Yes.
And like when that is put in like a substance or a cold substance, it begins to, I guess the best word would be evaporate.
It starts to evaporate. What is dry ice made of?
Good question.
I don't know either. All of a sudden you ask a good question, and I don't, give me 1 second. I'm going to Google it really quick. I'll find out.
Because I'm wondering if I can relate that to this. To
You can
kind of better understand it.
You can. Because what that means is that dry ice has a lower heat of evaporation. It doesn't require as much heat to change it from a solid into a gas. You don't even go through the liquid stage. Do you see that? Bear with me. I'm going to look up what dry ice is made out of.
I looked it up. It's the solid form of CO2.
Okay, so it's a solid form of carbon dioxide. Wow. Okay. So it is it's a polar molecule, but how is it being held together? It's being held together by partial positive and partial negative charges. Which aren't as strong as hydrogen bonds, right? Almost like a van der Waals kind of thing, but not so much. Okay, Kevin, that was a good, I don't think I may have learned that at some point, but it's been a long time.
They have them at like carnivals and stuff where you can get them, and it's like this, everybody calls it like the smoky drink because it just like evaporates. So I didn't know if it was like the same, like breaking down as
But
you would something
you know,
else.
the other thing that it does is it burns you. Have you ever like held a piece of dry ice in your hand? I remember my dad doing it when we make homemade root beer growing up. He'd sit there and run it in between his hands because if you're not careful, it will burn you.
Well, the phenomenon when I was going to school is people were putting salt on their skins and putting ice against the salt on their skin and burning themselves. So,
well, that's always a fun game.
Yeah, that was the big thing. But yeah, I just didn't know if it could relate or if it was kind of, you know, like the same thing with like evaporation.
It relates completely. What it's saying is that the hydrogen bonds in water are what's giving it a high heat capacity. or giving it a high heat evaporation. And carbon dioxide doesn't have that because you don't form hydrogen bonds. I'm going to remember that example. That's awesome. Okay. So a solution is a uniform mixture of two or more substances. The solvent is your dissolving agent, and the solute is the substance that is dissolved. Other properties of water. Water has a really good reactivity. We use it, we add water to substances, and we'll talk about this in later in this chapter. We add water to substances. Actually, let me put it a different way. We remove water from two things. We have monomers and polymers here. We remove water to take two, think mono is one. Monomer is a one subunit. We remove water to combine those two monomers into a polymer. Give me 1 second here. So a polymer oh shoot. Polymer is two or more monomers and think of monomers as being a subunit. Let's see, AKA subunit. Bound together, bound. A monomer the subunits. Okay. So polymer, think of poly as being more than one. Actually, let's not say two or more here. We're going to say one or more. So going back to our PowerPoint, and I know I don't type very fast, so I bet you have that written down before I can type it out. Two monomers come together, water is removed to form a polymer, which in this case is a dimer. Di meaning two. So this is one type of polymer. Dehydration, this is a dehydration because you think dehydration, you're removing water. Adhesion or cohesion. Adhesions, water adheres really well to, oh, I didn't finish this. Hydrolysis reactions, breaking up a polymer into monomers. You're adding water. Spend a lot more time on this here in a little while. But hydrolysis, sorry, dehydration, removing water, hydrolysis, adding water. Dehydration reactions are connecting monomers into polymers by removing water. Hydrolysis reactions are adding water to break up polymers into monomers. So hydrolysis, breaking up polymers by adding water. Dehydration reactions, adding monomers together to form polymers by removing water. Adhesion is the partial positive or the partial negative charges of water
Can
Oh,
you
we-
repeat what you said for dehydration reactions, like adding monomers together?
dehydration reactions are removing water to add monomers, bind monomers together into a polymer. Let me say it one more time because I changed the wording on you, Caitlin. Dehydration reactions are removing water in order to bind monomers together into a polymer. So bind them together. Hydrolysis reactions are adding water to break up a polymer. And in either today or on Tuesday, we will spend a lot more time talking about that. Adhesion is the partial negative charges or the partial positive charges of water adhering to substances that are not water. So when water adheres to plastic, it's the partial I'm not sure what the charge on plastic is. I would guess, I don't know what it is. But the water adheres to the plastic. Cohesion is water hydrogen bonding with itself. Cushioning is when we can put something in water to help maintain the structure. So kind of it's a protective thing. Because the hydrogen bonds can reform and break to protect something. That's the cushioning. I think water is a very good, if you drop something into water, drop it into a glass of water, the drop until it hits the surface of the water is pretty hard. It's a pretty fast drop into the water, but once it hits the water, it slows down. That's the cushioning effect of water. Think about dropping a marble into a glass of water. You drop it and it falls really fast until it hits the surface of the water. And then it slows down. That's the cushioning effect.
The adhesion, you said it's partial negative or partial positive, or is it partial
Either
negative
one.
and
Either
partial
one.
positive? Okay.
Either one. Specifically with glass, glass has a positive charge. So it's a partial negative charges adhering to it. But other substances can be partially positively charged and or partially negative or have a negative charge, and the hydrogens are more likely to adhere to it, a partial positive charge on the hydrogens. So either one. So a little easier thing to think about. Mixtures. Mixtures are substances of two or more components physically intermixed. Three basic types of solutions. We have homogeneous solutions, mixtures of components like gases, solids, and liquids. We have colloids that are heterogeneous, so they're not equally mixed completely. Colloids are also called emulsions, where the solutes are larger than those in true solutions. However, they won't settle to the bottom of the tube. Nevertheless, the individual particles can scatter light. The individual particles can scatter light with colloids, but the solutes do not settle out, and they're not acted upon by gravity to the point of where they're pulled to the bottom of the tube. Colloids also can exhibit what's called a sol-gel transformation, which is a reversible transformation from a fluid to a solid. For example, Jello is a colloid. Or cytosol cells is a colloid. Suspensions are heterogeneous mixtures with large, often visible solutes that settle out. They get acted upon by gravity and sink to the bottom. If you think about this, I know some of you have children. Or even if you don't have children, some of you have pets. They give you a medicine in a bottle and they tell you to shake it before you use it because it's a suspension. Sometimes I know with my cats, they give me a medicine that's in glycerol. I don't have to shake it because it's a colloid. It doesn't settle out. Differences between a mixture and a compound. Mixtures have a variable composition. You can vary the amount of each substance in a mixture. Compounds have a definite composition. You can't vary the amount of each type of atomic element in a compound. Mixtures are not chemically joined. Compounds are chemically joined. They're chemically bonded to one another. Mixtures keep their own properties. Each substance in a mixture, because it's not chemically bound, keeps its own properties. A compound has different properties based on what elements it contains. A mixture, each substance is easily separated. A compound, the only way to separate the different substances, and one thing that in this, you could replace this with atoms. So substances, atoms here, atoms here. That's a good way. I may have to remake this table. Each atom in the mixture keeps its own properties. In the compound has different properties because of the atoms it contains that are bound to one another. In a mixture, each atom is easily separated from the mixture. In a compound, it can only be separated into its elements through the breaking of the hydrogen bonds. Examples are air, of a mixture, air, seawater, moisture on most rocks. In a compound, water, carbon dioxide, magnesium oxide, and sodium chloride. Looking back at water one more time. Water ionizes. Remember, so ionizing meaning you can form ions. So you add two water molecules together, and one water molecule can take one of the hydrogen atoms off the other water molecule. Resulting in one water molecule that has an overall positive charge because of the proton on it. And the other molecule, this hydroxide, let me spell that. Okay, I'm going to give you a couple different terms here really quick. OH minus is a hydroxide ion. H plus is equal to a hydrogen ion or proton. H3O plus, and I'm sorry, I don't have ways to make uppercase and lowercase here that I know of, is hydronium. Ion. So that's the differences here. So in pure water, let me finish this out. This ionization of water results in the formation of an acid and a base. Acids give up hydrogen ions. Bases accept hydrogen ions. You'll see that in the next slide, I think. In pure water, the amounts of the hydronium ion, which is the acid, and the hydroxide ion, which is the base, is equal. So it's a neutral solution. The amount of positives match the amount of negatives. Acids and bases are electrolytes because they have that negative and positive charges on them. And they dissociate in water. Acids release protons or hydrogen ions. You guys, why are hydrogen ions called proton? Can we also say they're protons? Why can we say a hydrogen ion is also a proton? How many the atom itself, when we think of a hydrogen atom, how many protons does it have?
One.
One.
It has one. How many electrons does it have?
One.
So an atom that has a plus charge on it has how many protons over the number of electrons?
0.
Wait, let me say this one more time. An atom that has a positive charge on it, and you're right, I think you're right. You're thinking, you're answering my next question. An atom that has one proton and one electron, how would it get a positive charge? Caitlin, you know this because you kind of already said it.
But I don't.
How would it, what does it have to give up to get a positive charge, any atom?
An electron.
An electron?
It has to give up an electron. And in the case of hydrogen, if it gives up its electron, it's only a proton, right?
Right.
So that's why we can say that hydrogen ions are also protons. Does that make sense?
Yes, because it's essentially giving up the electron. So the only thing it has left is a proton.
Exactly, exactly. So so acids release protons or hydrogen ions and a negatively charged substance, which takes that electron from the hydrogen. So we give up the proton, but we keep the electron. Acids are hydrogen ion donors. Most common acids are hydrochloric acid, acetic acid, and carbonic acid. Hydrochloric acid, one of the most strongest acids out there. Acetic acid, what you have in vinegar. Carbonic acid is what you find in the blood. And we'll talk about that next time, but I'll talk specifically about carbonic acid next time. Bases, so acids give up hydrogen ions. Bases are anions, negatively charged, that take up hydrogen ions. For example, the hydroxide from the ionization of water will take up a hydrogen ion to become water. And I need to change this. Not all bases are dissociated anions. I need to change that. But all bases take up hydrogen ions. All acids give up hydrogen ions. The most common bases are the bicarbonate ion and ammonia. If you look at the chemical formula there of bicarbonate, what do you have to add to it to make carbonic acid? Look up here. What do you have to make? What do you have to take on for the bicarbonate ion to become carbonic acid?
More hydrogen.
One more hydrogen, and then it becomes an acid. So do you see the relationship between a base and an acid? A base takes on a hydrogen ion, and it immediately will become an acid of some kind. Some are weak, some are strong. An acid gives up a hydrogen ion and becomes a base. This is an equilibrium thing where it's always moving back and forth. But some acids are strong, meaning they dissociate really easily. They give up the hydrogen ion really easily. But they're a lot weaker in taking them back. And some bases are really strong, but they're less likely to accept, they're less likely to give up that hydrogen ion. This is one of the main reasons that some acids are so strong that they burn through things and they destroy things. Some bases are so strong that they destroy things because they denature by taking hydrogens or giving them up. They destroy things by taking them up or taking them up or giving them up. Well, you know what, we're going to end right there. Any questions or concerns? Hopefully we'll finish this chapter next week because I don't want to get really far behind and I'm a little worried. But I feel like this is more difficult stuff to understand sometimes. And I'm always learning how to explain it better and a little faster, but I'm not quite there yet. Let's do one more thing here just in the last minute. I'll just tell you this. pH is the measure of the hydrogen ion concentration. So pH is the measure of the hydrogen ion concentration. By a factor of 10 in the negative. So the greater the hydrogen ion concentration, the lower the pH. If you look here, pH equals into the negative log. The greater the hydrogen ion concentration, the greater the pH, the lower the hydrogen ion concentration. The lower the pH, the higher the hydrogen ion concentration. That's based on this negative here. Sometimes it's easier for me to think of it, and I'll write this really quickly. Be patient with me for 1 second. Let me write this really quickly. It's easier for me to think of this pH as being this. 1 over the H plus. So it's an inverse relationship. One other thing that we have to include here is that it's a log, which means it's a factor of 10. So the greater the hydrogen ion concentration by a factor of 10, the lower the pH. The larger the hydrogen ion concentration, so yeah, the smaller the hydrogen ion concentration, the higher the pH by a factor of 10. And I will see you guys next Tuesday. And we'll start right there.
Have a good day.
You too.
Thank you.
Thank you.
Yo, have a good day.
Alexa, are you there? Alexa?
Yeah, I'm here. I just forgot to leave because I'm.
You're
looking at
okay. All right, I'll talk to you later, all right?
Yep.